Howdy, everybody. I think everybody already knows me, but I got to remember to say hello to YouTube. So my name's Gavin Nielsen, and this is the seventh season or seventh session in the Coastal Defense Project that we've been working on. This time we're going to do lead time, predictors, and fire control. And the prediction algorithm is a nice long one, so that's going to be our big thing that we're going to get done today. We might have to do fire control in a session that didn't really happen. Like, what I mean is, like, might post something to YouTube that didn't actually happen here, just because of time, and we have to stop after today on software. I thought this was an interesting little cut. I think it's either from a newspaper or a magazine in 1943, but Battleship X sinks an enemy ship 18 miles away. We've been talking about this a long time. So, think what we think it's impressive now. Think what people thought in 1943. Like I said, this is the seventh day, the seventh session, and we're going to work on prediction and fire control today. Next week, we're going to hop into SolidWorks. You don't have to have or buy SolidWorks for that, but just curious, anybody already have it or planning on buying it? Okay. It's great if you have it. If you don't, just watch, and there's still a lot we can talk about. Yeah, Ron.
So is there a method for connecting to Inventor?
Yeah.
Okay.
Yeah. Simulink Multibody has an import mechanism that can pull in from Inventor and SolidWorks and other places. And in the worst case scenario, you can export from Inventor out to like STEP or STL or things like that, and then import. So there's ways around it if I can't find a direct connector. And then once we get the 3D model stuff going, we'll start hooking up circuits, electrical and hydraulic circuits to drive it. And in the final seminar, we'll see if we can hit something with all the stuff put together. So now for today. So most of the time we've been kind of doing the first, basically it ends up being the first half is theory and the second half is practice. We have a lot to do and we have plenty of theory to do it with, so we're going to spend the whole time practicing. It's kind of going to be a lab time this time. And so what we're going to spend our time doing is 4 things, and the first 2 should be pretty fast. The third one is a decently hard problem. But I simplified it from what I was originally going to do, because that would be a really, really hard problem. And then we may or may not get to fire control. Just depends on timing. Always seems like it takes longer to talk through something, so we'll see. Right, before we get to that, what's the motivation for that first bullet point in project work, a new ranging algorithm? How many times have we written a ranging algorithm? We've written that a couple times at least, right? We did the shell tracking one for 100 different shots. We did one last week that evaluated the range, and so that we can implicitly solve for our elevation angle. But the problem is that for us to hit the target that we need to as far as the accuracy of the simulation, so that we know what the accurate range is, and also at the same time make it computationally efficient, we need to repose the problem because of the fact that it's as I was working on it this week, getting ready for tonight, we'll spend so much time watching the simulation run, and we need to optimize our development of the algorithm too. So sometimes you'll find yourself remodeling something for computational efficiency, so that you don't have to wait so long. You can get to the answer faster. Does that make sense? So it's going to do the same thing. It's just a whole bunch more efficient computationally at doing it. So it's going to use a variable step algorithm with zero crossing detection, things we've talked about. So this is what it looks like. And I want to pause here and just talk through this. Normally our habit has been to start with a blank slate and have some interaction on this. But this is another one of those things that's simple enough. It actually helps understanding a lot more to stare at it for a second first. So when we kind of reposed, you guys recall the bouncing ball state chart that we did? And it had one state, right? There was a bounce transition and a state. Well, this is similarly sparse in terms of states. And there's a reset state, a splashdown state, and a flying state. And so what we're doing here is just making this super efficient and posing it in a way that the solver has to do the bare minimum of things, instead of having to run through and calculate, because our last algorithm calculated every foot of the flight of the shell, it was tracking it. So that makes for a whole bunch of solution points, and the solver's working way too hard. So what this is going to do, so in the reset state, here's the little default transition with the bubble. It sets the height and the range equal to 0, and the height velocity and the range velocity to 0. So that's in the curly braces is the command that happens along a transition. And then when fire 1 happens, it creates HV, it assigns the value of the horizontal velocity to these things. And that's during the transition, okay, when fire 1 happens. And then that's kind of like the initial condition. So remember we sort of took the projection of how high did we aim, and how much of that goes into the horizontal axis, how much of it goes into the vertical axis. That's what that is right there. And then it goes directly into the flying state. And the flying state continues to spin. That's kind of like one of our for loops or our while loops. And all that's saying is the HV dot, in other words, the horizontal velocity time derivative, is equal to negative gravity. So gravity was defined as positive, so we're calling it negative gravity to pull it down. And H dot, or in other words, the time derivative of the height, we're just assigning that to the velocity, the HV, horizontal velocity. And the same with range dot, is the same as range velocity. So we're just setting these things equal to each other. And all of this continues to run in a continuous way. So in other words, the solver is generating all the solve points for us. We don't have to say, track it every foot. It just says, hey, here's my max step time, and I'll track it, when I need to. It'll automatically generate the 0 crossing, and so that when our height gets below -2, in other words, we've kind of splashed down and it's in the ocean, it'll generate the 0 crossing, so we won't go too far past it. And that'll get us into splashdown state, and that's where we can report our findings of this is how far that particular elevation setting took us, and that will kind of set everything to 0, not H and R, because we need to know that stuff. So it actually puts the output H out equals H and R out equals R, and it'll stay there until we reset, and then the whole thing starts over again. So, any questions about that? All right. This is less obvious of how to do it. So this one I wanted to kind of start with. Here's a solution, because we're gonna rip out our old one and put this one in. But I still want to show you how to do it. So let's go to it. Okay. So we will go to 6. I'm just pulling the stuff that we worked on last time forward. Don't need reload. Don't need the ball stuff. Wait, wasn't it? Was it shell tracking play? Just making sure we're in the right. Yeah, okay. Shell tracking play. Okay. So we'll copy that and go to 7A, paste it in, and actually I'm going to rename it to shell play 2. Okay, so let me open this up and I'll just remind you of how long this took to run. Actually, I don't want to watch that. Let's watch the error. You remember we defined the error output as something we were trying to bring down to 0, and it would converge that way. So let's run this. Okay. So it's solving. So this is it's solving a set of ranges, but in order for us to get down to a reasonable accuracy, it still takes that's kind of about where we said about 5 feet is what we were shooting for last time. So that took something like 16 seconds in simulation time, but that took us 15, maybe 25 seconds of actual time. And really what we want to do is make this thing run a lot faster than real time, so that as soon as we get everything going, hopefully, we can actually run it at real time by slowing it down. All right, so let's kind of yank this thing out and put the new one in. So first thing, we'll create the chart. Let's see. Where did you go? That's what I wanted. Okay. All right, so there were three states. All right, the first one was reset. And remember, in continuous time state charts, there isn't really any entry or exit. There's just a during. So that's why there's the DU there. Complete equals 0. Okay. We also need to remember that we need to initialize these things. So we put the curly braces, H equals 0, R equals 0, HV equals 0, RV equals 0, and curly brace. Okay. Good. Then we transition, and the transition condition in square braces is fire1 equals 1. Okay. And then open curly brace. Now this is, remember, this is the part where we're just looking at what's our projection. So HV equals muzzle velocity times the sine. So the horizontal portion is the sine, right, of our elevation input divided by 360. Remember, we have to convert to radians, times 2 times pi. And then, let's zoom in just a little bit. Our range velocity is the same thing, but just the cosine. By 360 times 2 times pi. And I honestly don't remember if you don't put a semicolon here, if this will output, but just in case, that'll slow things down. The whole point, what we're doing right now, is for speed. So don't forget those. Like I say, I can't remember if how that's treated. Okay, so this is our state chart shell 1. Okay. All right, so this is going into the flying state. Okay, in that flying state, during that, remember anything underscore dot is the time derivative. So like x dot is derivative with respect to time. So HV underscore dot equals minus gravity. H dot equals HV, R dot equals RV, H out equals H, R out equals R. Okay, good. I'm going to transition to this state as soon as H is less than -2. Sorry? Say it again? Oh, thank you. Not too ambitious, too many R outs. Okay, thanks. Yeah, please do tell me when you see stuff. We spent 5 minutes on a simple little thing last time, so I'll try to avoid that. I can use the help. So here's a splashdown state. The during portion of that, we're going to set H dot equal to 0, R dot equal to 0, HV dot equal to 0, complete equal to 1, so we can signal that we're finished, and then make sure we still output H and R. So H out equals H, R out equals R. Alright. I'm tempted to just copy and paste models I've already made, but I think you guys miss out on a little bit when I do that, so that's why I'm not doing that. Alright, so the last part is transitioning back. So when my reset equals 1, pull this up so I can see it. Alright, open braces, H equals 0. Remind me, I want to make a comment about how to think about where and when you can do stuff in continuous state charts, in case I forget in 30 seconds. Okay. Alrighty. So the comment I wanted to make was, as you look at this, notice when I'm, so I have some continuous variables, right? H and R and RV and HV, and we're going to define those as continuous like we did last time again. But we cannot assign the actual continuous variables during the state, and we can't assign the derivatives during the transition. So I just want to point this out because it took me a second when I was going through this and debugging it, and it hadn't clicked in my own head. So I want to help it click in your head too. Because of this, remember how we were using integration in our Simulink models before, and this is kind of strange because this is defining the derivatives instead of the integrals, right? Well, think about how this is being solved. This is being solved through integration. And so it actually makes more sense if you look at it from the standpoint of the solver, saying, okay, during these states, so this is when time is actually taking place. This happens in an instant from a solution point of view. And then this, then this stays for a while. And then kind of in a time instant, this happens again. And so where the solution is actually taking place, where the solution is actually taking place, you want to be integrating. So that's where we are assigning to the derivatives so that we can integrate those. When you're changing between those states, that's where we're assigning to the continuous variables, because that's like, you don't want to be assigning them in the middle because then you'd have to calculate derivatives. In other words, does that make sense? We want to be calculating integrals, we want to be integrating, so when we're actually spending time solving during these states, we are defining the derivatives so we can take the integrals, so the solver can take the integrals. Okay, so question about that, or I'll move on if we're good on it. Okay, so I'm going to do Control D to update the diagram, and it's going to say, oh, there's unresolved signals. Okay, so a few of these I'm going to take off. All the dots I'm going to take off because they'll be implicitly defined, and those are all good. The outs need to be outputs, are they? Oops, are out. And that looks good. Okay. All right, now I'm going to go into the Model Explorer and look at the chart. And I have to update the diagram so that there are symbols in the Model Explorer to manipulate. So we have a few things in here. We know that MV is going to be, sorry, that's our input, HV rather, is a local, but we don't want it to be, where does that go? Complexity. Oh, I forgot. Okay. We need to make it a continuous state chart, right? Update method is continuous. And we want to enable zero crossing detection so that when we splash down, it generates the zero crossing. So hit apply. Now let's go look at HV. Okay, so its update method right now is discrete. We need to make it continuous. So we're just going to create, or not create, but redefine those variables HV, RV, H, and R as continuous so that the rest of this works right. And then the dot, the underscore dot of those same names will work correctly. So I'll do that. Okay, and that's about it. So let's do a Control D again, make sure everything's kosher. Is it okay?
Kevin, real quick, high level, what do we do?
No problem. We are, okay, you remember how we've done the shell tracking algorithm to track like 100 shells? And then last week we did a single shell tracking so that we could iterate to figure out implicitly what our elevation should be to hit a particular range. But that processing style of fixed time steps is very computationally expensive, and so our algorithm is really slow. So we're just, even though we've already solved the problem, we're remodeling it in a way that's more computationally efficient. So this is going to be able to use variable step solvers and zero crossing detection, and then we don't have to track the bullet or the shell every foot. It can go 1,000 feet between those solve steps. So, yeah. All right. So let's zoom in and just make sure this thing works like we want it to work. So we'll put a couple things in, some constants here. While I'm doing this, can anybody tell me why this won't work as is? Because it won't work as is. Let me restate that. This won't help our situation as is. But why? Anybody know why while I'm finishing out this?
You mean replacing an old module with this one?
Yeah. What was special, what was different about that module that we're replacing that this one doesn't have so far? You may not remember the detail. So, well, it's true that it doesn't have fixed steps, but we did that on purpose. You have a thought? Oh. Should I tell you, or anybody got any thoughts before I? Okay. So remember that one's accelerated in time. And so this one, as it stands now, isn't any faster than actually launching a shell to see how far it is. So this is going to take like 100 seconds of simulation time, which won't work because we need to solve this in like under a second for each solution. Does that make sense? So we need to take this model and figure out how to accelerate it. The problem is we're using the time solver inside Simulink. That's what we're leveraging here, right? So that we can have the automated zero crossing detection, so that we can use those continuous states and not solve so many things. So we kind of need to hack this a little bit. We want to represent the same thing. We just need to trick Simulink into solving it a whole bunch faster than reality so that we can get our solution faster. So I'm connecting this up. Any thoughts about how we might be able to do that? Took me a while staring at it, so don't feel bad if it doesn't come to you real quick. Okay.
You have to change, excuse me, somehow you have to change what time means in all of your other variables, right?
That's one way we could do it. I found a simpler way to do it that doesn't mess with everything else. But I just want to approach this gingerly. Okay, what is it that we're waiting for to happen? We're waiting for the shell to hit the water, right? So the reason the shell actually ends up hitting the water is because of gravity, ultimately. And so if we accelerated gravity, then the shell's going to hit the water faster, right? So we can accelerate how long this whole thing takes by a certain amount if we just accelerate gravity. So I'm going to put in this 32 here. Let's say we want it to be 10 times faster. So gravity is now 10 times what it normally would be. But now the problem is the reality factor. Now gravity is 10 times more, or like on Jupiter or something. And we shoot, and it doesn't go as far. So
You get times distance.
we just multiply the distance times 10. So there. Now we can multiply how fast. We're solving the same problem. We're just reposing it to simulate. Does that make sense? Okay. All right, so we are not going to reset, and our elevation, just so that we can try this out, is 20. And we will fire, and our muzzle velocity will be 2,500 feet per second. Okay, now, so this is a continuous state chart, right? And we have we're more used to setting a step time explicitly, but you can't set a step time. It's what we're trading, right? We're making this a variable step solver. We don't want to mess with all of. We could go go into the configuration parameters and set our maximum step time to be something small. But what about all the other stuff? We don't want to mess with the other things. So we could put in here our max step size is a certain amount. We don't want to do that. Because of the fact this is inherited, we can actually drive it from one of the things that's driving. Okay, we're trying to drive this state chart to solve at a particular speed. So we can drive it by making something else that's feeding it at a certain speed. Okay, so I'm going to have it just for the moment 1 over 1,000, just as a starting point. Okay, so let's look at h out and solve. Cross our fingers. Yay, it worked. 5 minutes is an eternity, by the way, when you're trying to solve a problem up here. And that took about 5.5 seconds, so that makes sense, right? We're supposed to speed this up by 10 times. And 50 seconds is a reasonable shell. We're launching at 20 degrees elevation. And I want to show you real quickly, whoops. We'll go into the plot parameters and change so that we can see the points. So if we zoom in just a little bit, we can see there's still a lot of points. We could maybe slow it down a little bit more. Okay. So that's all good, but I want to mask this so all the details are taken care of for me, and we're done. Kind of be done with it. So let's pull these things. Fire 1 and muzzle velocity. Okay, I'm going to mask this very quickly so we can use it. Get out of there. Okay. First, make it a subsystem. Right click, mask, oops, create mask, and I'm just going to add a couple edit boxes and say this is going to be the, what do we want to call this? multiplication factor. How about the speed factor? That sounds better. Call it SF, and oops. Sample time in seconds, TS. Okay, that's good. And that way, this is nice and parameterized inside here. I'm going to go in and set our sample time here to TS, and SF is a speed factor, SF is a speed factor. Okay, now we've abstracted all of that, and when we double click, we can look at it that way. So this will solve our problem a whole bunch faster. Okay, so let's pull this out and put it in to our shell tracking play 2. It's going to go right in place of this one.
Isn't that speed factor also going to affect the height of the equation?
It will, but for this, we don't care about height. All we need is time of flight and position out. Right? So, oh, and that reminds me, we've almost forgot to put in time of flight. So let's grab this and put that back in. Close, huh? What's that? Okay, so I'm going to delete this and grab that, where'd it go? State chart shell, copy. Oh, we also need to name these things so we can figure out what they are. So this is elevation, my reset, gravity, fire 1, complete, range, and height. Okay, so how do we, how should we look at the time taken to do this? So we want to know the difference between firing and getting to here. So it is, let's make a new internal variable, fire start equals 0. Let's see, how's best to do this? We need to figure out what is, sort of make a marker in time for the starting of the time of flight and then the finishing of it. So I guess we're looking for integration. So if we integrate by 1, that will start to accumulate time on the tracker, right? So we can say TOF equals 0. During the flying state, TOF dot equals 1. So it's accumulating time. And then right here, TOF out equals TOF. Okay, so we got to resolve these symbols. So I'm going to hit Control D. We don't want the dot because that's going to be defined. So we'll go back to the Model Explorer. Get this thing going. TOF is now going to be a continuous variable, and it's all good. Okay. All right. Okay, but we also have to scale up TOF out by scale factor because that's the whole point of this, right? We need to know how far it went and how long it took to get there. So WTOF. So we'll save this. All right. So make sure everything resolves right. It says, oh, yep, wasn't listening to myself. I need to set that. I can't set, because it's a continuous variable, I can't set it inside there. So I just need to set it here. Very good. B. Time to upgrade the computer. Okay. All right. Copy this guy. Shell tracking play 2. Put it in here instead. So we want, this is elevation, plug that in. Plug in reset to my reset. Fire 1. All right. So we don't need this anymore because, did I get it wrong? Oh, thank you. Good. Okay, we don't need to, we're not outputting 3 vectors, or excuse me, a vector of 3 for the position anymore, so we don't need that. But we can say our range out, that's complete. We can say our range out is here, connect that dot. We don't really care about height, which is fine, but we can also see our time of flight, so we'll make sure that works. All right. So remember, we did this just a little bit ago. It took like 25 seconds to do one solution. So let's try that again. Let's go to the error and see how long it takes this time. Come on. It's done. It's a lot faster. Okay, I'm going to have it run for, instead of infinite amount of time, because that's really fast, 20 seconds of simulation time, and then look at this error. Okay, 10 seconds, because that, I don't want to reset the window. Oh, did I not do fire 1? Fire 1's there. AP. Spent plenty of time making sure that this goes through these states last time. So I'm pretty confident about that part. Shell 1. Oh, where did it go? Alright, here's our shell tracking play 2. Maybe I accidentally closed it. Okay. So we had elevation try. So let's look at our height and make sure we're flying. Okay, 10 seconds. Oh. Aha! Speed factor. 1,000. Sample time 1 over 1,000. There we go. Boy, that gets me every time, doesn't it? Okay. super fast. So we're finally back up to going faster than real time again. I'll just run it again so you can watch it. Far, far more computationally efficient. All right.
It's like just over a second.
What's that?
It's that graph like completion state versus.
Oh, that was one solution took 6 simulation time seconds. Yeah, we can turn up that though as we need to. In fact, we'll turn it up a little bit right now. We'll make it 10,000. That way, this error should go there very quickly. We have to make sure that this is running fast enough to deal with it. Come on. There. So we're making the solution much, much faster in simulation time now. And I think this doesn't need to be 10,000, probably 1,000 is okay. Okay, good. So now we have this. Now let's move on. Any questions about this before I move on? We beat it to death pretty good. Now, the next thing we need to do is our lead time calculation. So the challenge with lead time is that you need other things. It's like a simultaneous kind of solve deal. So when you're thinking about lead time, you also need to know what your range is. Like, well, how long is it going to take me to get there? What's the time of the flight? Because obviously my lead time is going to be at least the time of flight of the shell, right? Otherwise it's going to miss. But I also need to know the predictions. And when I change my lead time, then I'm actually changing my prediction, which is going to be changing my time of flight because I'm shooting somewhere else. So that's the interesting thing about this problem is there's a lot of simultaneous solves, but we can do this the same way we just did ranging, or excuse me, ranging. So we can implicitly solve this by wrapping another loop around it. So make sure I covered everything here. This is, I just like the picture, but the target's a boat, and this one is launching a torpedo, and so they're plotting a solution to the impact point there. Yeah, without knowing the time for a particular range, we can't calculate lead, but without knowing lead, we can't calculate the range. All right, so we know that we're going to be producing predictions in a fixed time step ahead. So for us, I was thinking back to the movies I've seen. That's a great place to start from a reference. And I was thinking, yeah, you see the radar. It's kind of a ding, ding. That's about 1 second. Okay, so let's just assume that the radar is delivering to us our range and bearings for the target at 1 second intervals. Okay, so we're going to do prediction at 1 second intervals, and that's going to lead us to a nice integer shifting of figuring out, are we going to shoot in 3 seconds or 4 seconds or 12 or 13? We're not going to say we're going to give them a 13.5 second lead time. And then what we'll do is we'll schedule the launch so that it's exactly when we want it to be. Does that make sense? Okay. So we'll round our solutions to the nearest second. We have to build in a buffer, like I said, so that we can take the shot. We have to have a little extra time so that our fire control can make a decision. Because if we give ourselves just enough time to fire the shot, then there's no time to wait and actually make sure everything's lined up and pull the trigger. So there's a buffer, there's a particular prediction range we want. Like the other solution, most of the time in this is going to be waiting. Just waiting for the other things to finish and then trying a new thing. So we're going to do that kind of implicit control system again. So what we're going to do is, this is our range calculation, the one we just finished and optimized. We're going to take that and we're going to say, okay, we're feeding in the error and the time of flight and whether or not it's complete, and feed it into a new chart. And the new chart is going to figure out, Okay, this is how long it takes for this range, for this lead time. This is the time of flight, so I think our lead time should be such and such. Okay, over here, we haven't finished the predictor yet, so we have a vector of predictions. And the chart is going to be able to change which one we pick. So the way I define this here, it's there's 200 predictions, and they are all multiplied by 50, so that's the offset. So in other words, it's what we're assuming with this thing is every second it's going to move about 50 feet. And then we're adding to that this is out at about 22 miles. So we're changing what's our predicted range based on what's our lead time. Does that make sense? Well, what I'm saying? The longer we take to shoot, the further they're going to move. So, okay. This we haven't talked about, but this is a selector, and it just allows you to take an input index as a port and a vector as a port and select one of them. And that's what we're going to feed into the range calculation as a reference. So again, this is what we just did, this little box. We're just sort of zooming out and wrapping another loop around it so that we can do our new solution. And this is what one solution, and I think it's probably easiest for us to just copy and move forward with this because it's exactly the same idea as what we did on the range calculation. So for this, we're going to try a particular horizon, and then after 1 second, after everything's had time to initialize, we're going to wait for a solution, and then we're going to watch the error, just like we were doing before. And as soon as the error gets below some maximum error, then we're going to calc a horizon error. So we have a couple errors now. There's horizon error, which is what this is doing, or lead time error, and there's range error. So we're watching range error. Stick with me here. We're watching range error so that we can reduce lead time error. Okay? As soon as we calculate an error, it's the same kind of thing. We're just going to use a proportional controller implicitly. There's two little feedback loops here. If for some reason we're going in the wrong direction, and our horizon's less than 1, that doesn't make any sense. So we're going to do it again. We're going to go back. This transition goes back to the same state. If in case the horizon is more than the maximum lead, like we're not predicting past 200 seconds, for example, then essentially what the algorithm is saying is the ship's out of range. Don't try to calculate a horizon for that. We can't think that far ahead. So in either of those cases, if it's between 1, as long as it's between 1 and 200, then we will try the modified horizon and actually output a new horizon. As soon as it outputs that new horizon, then that'll go in. Let me back up once so you can remember. That'll go out here and come back in and give a new range to the range calc. And then this goes again. So most of the time is going to be in this wait for solution state. So this doesn't have to run very fast. It just needs to be careful about what it does and make sure that that K value isn't too high. Because remember how the last time we had a K value and it was like 1e minus 5 or something like that, or 7e minus 5. It was a small value. This is another value that doesn't have to be that low, but you don't want it to be too big, because then you're saying, hey, check this range, check this range, check, you don't want it to hunt around either. Okay, so if there are no more questions with this, I'm going to keep rolling. Try to get this one done quickly too. Okay, that's the one that's done. Okay. It would be easier if I just take our shell tracking play and save as, because we're going to wrap something around it anyway. Okay, and this is going to be lead calc, we'll call it lead calc 2. All right, so we're going to take all of this stuff, and we'll leave that one in. We'll take all these out, and we'll kind of make this another subsystem. Oops, didn't mean to do that. And let's see. Good. So just making that one little click right there, that's a really powerful one click. That's kind of like dynamic refactoring of the model. We decided, I don't want to look at all that junk anymore. Put it in a box, put it away, and that's kind of like the dynamic, like writing a function and copying and pasting all the code and making sure all the parameters work. That's one of the things about Simulink that's pretty great. Okay, so this is range ref. Coming in. I don't think we care very much about heights. I'm just going to terminate this guy. Come on, terminate. And we care about time of flight. Time of flight. And we care about error. And of course, we care about elevation. That's one of the reasons we made this thing, right? Okay. All right. So now we have a subsystem that does elevation and time of flight. So we need to feed back into that. This is our range reference right now, but we're going to feed back into that something else. So let me pull this over here, and then there. Okay. All right, so for our predictions, we're just going to take a constant, and we'll do something similar. So I'm saying 1 to 200 predictions, and multiply those by 50, and then say 22 miles times 5,280 feet in a mile. All right, so that's a nice big vector, 200 element vector. We don't need this anymore. And we need a selector, right? Whoops. Not that kind of selector. Oh, actually. Yeah, we just need to change this. Instead of being a dialog-based thing, we'll make it an index vector from a port. So now it'll put the port on the outside. We also want to dynamically adapt to how many things are coming in. So we'll make it -1 to be inherited instead of explicit. And we only have, it's a 1 by n vector, so our input number of dimensions is just 1. Okay. So that's the whole vector coming in, and then we're going to be telling it which one to pick when it comes back out. So right, we have that. Now we need a state chart. So add a state chart. Need a memory here. And we'll inherit the sample time. This is just to break the algebraic loop, right? Because of being able to, can't solve everything all at once. Okay. So the first thing we're going to do is try a horizon. And during that, remember we're back into discrete time state charts again. So we want to do this on entry. We want the horizon to be equal to, I guess we're talking about it like lead, so let's try to keep our, try a lead. Lead out equals, so we're saying 50 seconds of lead time. And equals 50. So we're differentiating between an internal variable and our output port. So lead out equals lead. Okay. Now, wait for solution, where we don't really do anything, just waiting. We'll do this. Come on. After 1 sec. So that's solution time, simulation time, 1 sec. And then we have calc lead error. And on entry, error equals time of flight plus, remember we need that little bit of a buffer in order to make a decision. Off, buff. And here's our reference minus what we currently have. So that's why we put in horizon here. Horizon. Sorry, lead. Error equals 2f. So lead is what the current value is. And then horizon, it's going to keep getting me. Lead equals, this is where we're using the round function because we need it to be an integer number of seconds. We're saying horizon plus the error times k. Yep, I do. Thank you. All right, good. That's all we need to do there. And then try mod lead on entry, horizon, nope, okay, just gonna get me over and over. Lead out equals lead. All right, so when I'm looking at this, I really just, I want to transition for normal reasons. Wait on the solution until error is less than max error. That makes sense. Try this. You don't have to go try a new one until your error is, if your solution is already still good, you don't have to go anywhere. So we can transition on error greater than max error away from that. Does that make sense? Because there's no sense in shifting things around. Yeah, that's good. So, this is going to be, we need to do our checks here. So this goes back around if lead is less than 1, and this also goes back around if lead is greater than max lead. Okay, so there's the first one, there's the second one, there's a 1 and the 2, and if neither of those evaluate to true, it will unconditionally go to try the lead. Okay. I think that should do it. It's good. So let's update the diagram. I'm pretty excited. We're almost exactly on time. That's brand new for me. All right. So max error, an input, buffers an input, time of flights. Time of flight actually is a output. Nope, that's an input, isn't it? Almost forgot. K is an input. Max lead time is an input. Lead out is really our only output. Lead, that's a local, and error is a local. Perfect. Okay. So now we've got all of our ports. All right. So, what happened to error though? Error is less than max error. I did. Error is internal error. Ah, so this is range error. This is, yeah, range error. I keep straight the fact that they have two different errors that we're working with. So range error should be an input. Okay. Now let's connect the dots on this guy. So time of flight comes out of time of flight. Range error comes out of error. The rest of these are constants. Okay. So let's say maximum error. Let's say we need to be within 10 feet. Let's say I want 3 seconds to make up my mind, or the fire control to make up its mind. So buffer of 3. Our maximum lead right now is at 200. And I'm going to cheat. I'm pretty sure 0.1 will work. Normally you'd have to iterate through this, but just for the sake of time. All right, so that's good. Now I just need to connect lead out to the memory, update the diagram. Is everybody following what I'm doing and why so far? Not doing anything too fast or too mysteriously? Okay. Say what? Okay. So it says we're good. Let's see if we're really good. Oops. Scope. Let's look at the lead out there. So that's how many seconds prediction. I also would like to see, let's put it on A, yeah. I'd also like to see our errors going on. So let's get both of these things going. And set this to, I don't know, 1,000 or so. I hope it doesn't take that long, but just so we have some time to watch it. And hit go. Mm-hmm. $1,000 was a lot. So, okay. So let's try something more like Calc 2. How about 30? Well, according to this, we are happy. Well, one step. I guess we were starting a lot closer than I expected we would. Let's try a little further away, just so that we make sure this iterates correctly. About 20-second lead time. And actually, let's bring this up here so we can look at it. I want to make sure this is not leading us astray. Ah, I know why. Okay. This should be error. Sorry. Not range error. Yep. Yep. That's true. Ah! The horrors of public presentation. Mismatched error greater than max error. Thank you. It's funny, it's like you get blind to certain things. That's alright.
Well, it automatically puts those in, but apparently you can delete one.
Yeah. Yeah. Okay. The data error was read before being written to. Okay, we just need to initialize it then. No problem. Let's make it a little bit bigger. Okay. This one should be range. Sorry. We'll get it. And our internal error actually we could transition unconditionally here. Just always be waiting on a solution. That wouldn't hurt us at all. It might hurt us a little bit. Okay. Let's back up from this problem and take a look at it again. All right. We know that we want to minimize the error coming out. Right? It gets down below a certain level, and that's what helps us transition to here. So then we calculate our own error and move into trying that. So that's when we change our lead out. Now we have to give this a little bit of time, so I think we need to add a little bit of time so that the solution will wait. I'm just wanting to make sure I'm not forgetting something silly from this. Range error greater than max error. So we'll add in an event. So I'm going to say after well, sex is not the right word, right? After 1 second. Okay, so sec is referring to simulation time. I will say 500 milliseconds, ms. I just don't want to wait a whole second. Now, when I recompile that, it's going to say, hey, we have unresolved symbols. Okay, fine. Yes, that's an input. Very good. So we'll go back. Here's the input. I need a limited counter. I'll call it or limited, I guess. And this will, upper limit is 1, sample time 1,000. And in order to make sure that this actually goes at 1,000 hertz, we need to look at the lower and upper edges. So we need to turn that on in the model in the browser here. So that is chart, MS, want rising and falling, apply. Okay. Good. Okay. Alright, so let's see why. This should be shifting the output. I close some of these because it's big. It's our lead time calc. Good. Okay. So we should be shifting this horizon. Which I don't think it's actually shifting. So let's figure out why that's is or isn't happening here. But if we can't solve this one quick, we'll move on. We'll get some prediction stuff done. So it's 50. Lead time calc. Goes through. Lead out equals lead. Error. Okay. We'll come back to this. I'll figure out what's going on. The idea is that we iterate and numerically solve the range, the elevation, and the time of flight, and then in an outer loop, we resolve the lead time, and that's how we can decide which prediction to handle. So sorry about that. We'll figure it out. Oh, I see what I did wrong here. That's a big no-no. There we go. Yeah. All right. Let's try this one more time. Okay. How's about, oh, okay. It's saying you can't send a 0 to a selector because it's 1 based. So this is initialized with a 50. Oh, okay. It was just a warning. Good. Okay. Well, we'll come back. It's tricky. You have two numerical solvers going, and they both have stability issues. So if you try to solve one too fast, the other one does this and that. And I'll have to look and see why that one's not going like it should. So in the interest of time, I'll solve this and then post it on the internet, and you guys can check it out. But let's jump to a more exciting thing of target prediction. Okay, so kind of reset your mind again. We were talking about lead time, but we're gonna jump forward to target prediction, and this is a little bit more exciting, I think, because it's you're trying to predict the future. I mean, that's what it boils down to, right? And so it's always unsure but you want to do as much as you can to like be able to get that as close as you can, right? And you need to check yourself too. So the issue is, of course, we've hammered this a little bit, like how we have a time of flight. We know we have to predict forward. What I was originally going to do was make 25 predictors and then pick which one we use, which is super interesting to watch, and I'll show you a picture of what it looks like to watch. But before we get there, the way we're going to do the prediction is least squares fitting. And so if you're not familiar with that, I apologize. I encourage you to get on the internet and read about it. But basically, it's a linear algebra thing. If you've ever gone into Excel and plotted some data, one versus x versus t or something like that, you're looking at stuff, and you want to put a best fit line or polynomial, something like that. That's what we're doing the math for on the back end here. So I thought, well, the best thing would be if you have a whole bunch of different predictors at looking at varying ranges back in the past, some looking like maybe 10 seconds back, some looking like 30 seconds back, some looking a couple minutes back, and a range of predictors of polynomial orders, because maybe linear, maybe a line is the best way to predict someone that's doing this all the time, because they're really forming kind of a long-term line. Or maybe if it's a real slow sinusoid, like a third order or fourth order, can capture some of those sinusoidal curves, right? So what I'm going to show you next is 25 different predictors. So on the left-hand side of this is the input, and it's trying to predict the right-hand side. And so there's first order through fifth order with 5 different buffer sizes. And what we're doing, we don't know what's going on the right-hand side. We're inputting a sinusoid, which is not polynomial, right? And so when we're changing the phase, just to show you kind of how it would look as you roll along, because that's what this is doing. It's continually predicting. So this is fun to work on, but
It's predicting the polynomial vector.
it's predicting the xy coordinates. So this is just one of those. So if you look at this, you can see it's kind of it looks like there's some things tangent, but it's just the further back they go, they are, like this one is the longest order, the longest buffer, but it's first order, so it's looking at probably almost the full half. This guy right here. And the other ones that kind of come up further aren't looking at as much of that curve. And you can see, so they're going in and out of, I'm doing a good job, I'm not doing a good job. And let me go back and forward again. As we as history transpires, right, we're seeing what was the future as we move forward. So what we're going to do is look at all those future predictions, store them in a buffer until that time really comes to pass, and that gives us historical. It's kind of like watching weather predictions and then charting which station was right. Okay? What's really tricky about this is numerical instability of switching predictors all the time. There's 25 different predictors. It also gets really complex because this, as it stands, buffers 500,000 data points that we have to search through in like a 4-dimensional array. So what I want to do to simplify that a little bit is just do one predictor, and we'll go through the stages of doing it. Yeah.
How much computing power was necessary for that? How long did it take to get this video?
Oh, that was running in real time. That was just a MATLAB script. Yeah. It looks cool. I mean, and you probably would do like higher fidelity if you were actually doing the algorithm, but I just wanted to help you visualize, because it's kind of an abstract thing. You guys are all smart people, but it's good to visualize things. So what needs doing? Like, how do we get there? We know we're taking in points, like xy coordinates. We can think of them as xy coordinates. We're actually getting range and bearing, and you all know that's just r and theta. We can convert that to x and y, no big deal. So what are the steps that we need to do to actually make these predictions? So the first thing we need to do is we need to make a trailing buffer to keep however far we want to look backwards to use for the least squares prediction. Maybe we want 20 seconds of data back, right? So we need a 20 sample long buffer for time and a 20 sample long buffer for that position. Then we need to take those two buffers and every time step shove the whole buffer into a polynomial fit algorithm, which actually Simulink doesn't have the kind we need. So we're going to kind of hack an algorithm and look underneath the mask of a Simulink block and create it the way we need it. Because they have, I'll show you, we just have to work around what it does. Okay, so that now we have a set of coefficients, right? We're going to do a second order. So we have 3 coefficients. We need to evaluate those coefficients for future times because we're trying to do prediction. So now we have a set of predictions. Like let's say we want to do, I don't know, we did 200 before. Let's say we want to do 200 predictions into the future for the next 200 seconds. But we have to keep track of all those 200 predictions. So all those vectors are going to get stacked into a matrix. And that matrix is going to be the historical future predictions. And then in order to quantify the accuracy, as time goes by, we'll compare what we predicted would happen with what actually happened. And that's the last step. And that way we have the fire control has some kind of a quantifiable confidence level. Like, you know, basically maybe they're zigzagging out there at 20 miles, so you need such a long prediction level that you say, hey, at 100 seconds, you know, for the last minute, I've been 2 miles off. Well, we probably don't want to take the shot. Like, that's not predictive enough. But maybe they're just sailing in a straight line. And so for the last minute, you know, the polynomial fit has plotted that line. And so it has historical accuracy of, hey, they're right where they're supposed to be, right on that line. Okay, the fire control then has some confidence level to take the shot. So does that make sense? That's what we're doing. Okay. So I told you it's a little more pipelined kind of a thing. This is what it actually looks like. And maybe it would be easier if we, instead of building it from scratch, I'll walk through what it looks like, so that we don't get hung up on something little, and so that you guys can see the nuts and bolts of this. But this is at a high level what it looks like. So I just pointed out steps 1 through 5. Here are steps 1 through 5. All right. So let's open it up and take a look. Full prediction 2. Okay. So because we could put in a sinusoid, but then it's a lot more difficult to know if we're doing a good job of prediction, because we know with a second order polynomial we can't capture all those dynamics. So to start with, we're just going to have a ramp as an input. So it's going to generate a line, like they're sailing in a particular direction, but they're not holding still. If they're holding still, then the whole thing, why do we care about prediction? So the ramp is kind of the next easiest one. All right, so the first thing is we want to buffer these historical positions. So I'm going to look underneath this. Let me do that a little bit slower. We want to buffer those positions. This is not tricky, but I want to show you what I did, because this stuff doesn't exist in an easy way. So here's the code that's running. We have a buffer out, and it buffers it, pulling the new x value on, and the buffer length is n. Okay, now I know that most of you guys who have been here consistently will be able to look at this and be like, oh yeah, I can write that. That's not a big deal. But there's one aspect of this that isn't apparent until you try it, and that's the fact that you're defining a size with a parameter, an input, okay? And you have two inputs here, x and n, yet when you look at the function, there's no n. The reason that is because Simulink will complain and not let you do that, because it would be as if you could dynamically change the size of the buffer, which you can't. At least not with the stuff we're going to do. So how do you get around that? The way you get around that is looking at, here we are, buffer 81. So X, now we're looking back in the Model Explorer because we need to look kind of with a more fine-grained eye on what the properties of those parameters are. And X is an input, it's port 1, we could change its name or its size or anything else. N is, we just changed to a parameter. So it's not an input port. And that allows us to parametrically change it, but only at design time, not during the run. So that's why this little tunable thing is not checked. That means you can't tune it, you can't change it while it's running. Does that make sense? It's a straightforward thing once you know about it, but if you don't know about it, how do I get around this? All right. So I'll back out one. We also want to make sure that we can know what our sample time is, because it's really critical that everything is synchronized. This whole thing is working off a 1 second sample time, so we want to make sure that's synchronized. So right now it's 13 seconds. I'm using lower numbers because it's easier to debug as opposed to a 200 beat buffer. So we'll just leave it at that for the moment. So that's that. Now, here's the part that is an interesting, I call it a hack. It's not really a hack, but so if I search for poly, I just want to show you what the issue is and how you can get around this sometimes. I would like a fit, polynomial functions. So least squares polynomial fit, right? And it would be awesome if this just did everything we wanted. But you'll notice it only has one input. And so as I look and I open it up, the control points are basically what we would think about as time. It has fixed as a parameter. But we need to kind of unwrap that and use it and kind of convert it to an input port, because our time is shifting all the time. As time goes by, we have this moving window of time and values. And then we can input the order. So, yes, I did go through linear algebra and some advanced math stuff, but I don't remember how to pose. I don't know if you guys are in it now or if you've been through it or about to go through it, but most people, unless they're doing this all the time, do not remember exactly how to set up the matrix so that there's an efficient solver can go solve it. So what did I do? I'm just trying to expose. It's not a matter of bragging. It's almost the opposite, really. How would you go about solving something that you don't remember how to do or you're learning how to do, right? So take this polyfit function, click on this little underneath the look inside the mask. I'll click on that. Okay, so the QR solver does have A and B inputs, but it forms a constant here. So it forms this V constant. I think it's called the Vandermonde matrix. It's just a certain way of setting up a matrix to feed in. And then this is our Y, or our position, okay? And we're not trying to be too tricky about all the signal attributes, so we can leave these things out. And this QR solver is what does the magic. Well, so what's this V? We didn't put in a V. There wasn't a parameter for a V. So if I hit escape again, I'm going to right click and go to mask and edit. Come on. View mask, base mask. There we go. Okay. So here are the different things, right? Control points in polynomial order. Now initialization is the interesting part. So this is where it takes n that you put in and x as a port, and it goes through. I wish it wouldn't do this because it just makes it hard to read. So let's just expand it a little bit so we can have different statements. All right. If that's the way you're going to be, I'll go somewhere else. I'm just copying and pasting it in here. So there's a statement, and then here's a for loop, and here's an end. So it's forming V right here. And that's the Vandermonde, I guess is how you pronounce that, the Vandermonde matrix, based on the order and based on the control points. So all I did was looked at this and said, well, that's not hard. I can copy and paste that in my own little MATLAB function block. And so if you look in here, I just said, what's the order and what's the sample time? And I remasked it. And I created a Vandermonde matrix block. And all it is it's pretty much the same thing. That same initialization code. It's just, instead of doing it once during initialization, it's doing it at every sample time, every simulation step. So that way, is everyone with me so far why I'm doing this? And we're kind of down in the nitty-gritty details of something. I don't want us to lose context. So if I back up out of it, this let me put in a particular order and a particular sample time. So here's one mask. I'm going to back up again, and here's the other mask. So that way I can feed in higher value mask parameters down into the lower mask. And that's the name of the game with abstraction. So I had it set to 1. I think I'll change it to 2. So we can't change it at the time of, in the middle of the simulation, because you can imagine then the matrices wouldn't match up as it was going. But we can change it here before we hit run. So as far as solving the problems of this beyond just visualization of it, that was the hardest part about this. And like I said, managing 25 of these is not hard once you get one going, but it's hard to get one going first. And so I didn't want to spend too much time trying to get 25, and then it's just a sprawling mess, Okay, so now we have this second order system, and I'll update Control D. So the second order system has 3 coefficients, right? X to the second, X to the first, and X to the 0. So this should be 3 by 1, which it is. And this goes into a polynomial value block. So these are the coefficients that we'd like it to use to evaluate a polynomial. And this is off the shelf, directly out of a Simulink library. But here's what it's doing that's a little bit different. I'll zoom in a little bit. It's taking simulation time, and then it's adding a vector to it. And so it's adding 1 and 2 and 3. So it's generating a vector on the other side of the sum block. So you can think about the vector that's going in here as simulation time plus 1 is one element. Simulation time plus 2 is another element. Simulation time plus 3, like that. So that is the future times being evaluated by this function. So it has our past data, polynomial fit, and we're feeding in future times to what we're predicting should happen. Okay, so that is feeding out a vector that's 10 rows long, 1 column wide, right? Because we have 10 different values. But we need to take that vector and stack them next to each other so that we can look back in time. So I'm going to switch back to the slide so you can see this. Okay, so where on the one hand we want our last prediction to be last in the row, we want our oldest prediction, so our newest, our most recent prediction to be first in the columns. So the oldest predictions are to the far right, and the future predictions are at the bottom. What that does is actually pretty cool. It means that for the current time, our diagonal is all of our predictions. So let me put this a little bit differently. At time 1 second, so the very most recent prediction we made, which was 1 second ago, that's this column vector. And that one was predicting 1 second into the future for its first element. So that's our first, that block right there is our first prediction. Okay, but 2 seconds ago is this second column. And 2 seconds ago, that column predicted that in 2 seconds, which is the second row, it will be such and such a time, such and such a position, and so on and so forth. So we can make this 10,000 long, it doesn't really matter. But the beauty of it is we can extract the diagonal out of this. And so as we shift more vectors in, we just get a new set of diagonals each time out. Does that make sense? It's kind of pretty. I didn't know that this was going to work out this way. I was hoping it wasn't going to be too ugly, and it ended up being really nice. And so the way this gets solved in the Simulink diagram, so you have this this buffer, which is pretty straightforward. I'll show you real quickly. Same kind of thing. We're just putting in x in the beginning instead of in the end. So that's the vector that's getting fitted in there. Now, looking at the truth and prediction, I don't know. That's pretty beautiful to me. We take a 10 by 10 matrix, or it could be any size really. We extract the main diagonal. We take truth, which is our current position at the current time, and subtract the two, take the absolute value, and that's our accuracy metric. I think it's pretty nice. It makes it kind of neat. So that is the prediction algorithm. And so I'm glad we didn't try to build too much of it. And that is what is going to be, so the polynomial value out right here is what's going to be feeding in to our lead calc right here. As soon as the numerical stuff gets solved and whatever little bug there is. Does that make sense? So now all these things, there's three major things going on that affect each other. There's, well, the prediction isn't really affected by it. That's really just what's going on with the boat. But the lead time, the time of flight, the range, elevation calc, all that stuff is going to be solving. Meanwhile, the whole time, there's two predictors looking at the XY position of the ship. And as long as we're in range and we have enough confidence with our predictions, we can take the shot. And the fire control then, we'll just look at that briefly, is really kind of a, almost get tired of looking at this wait for solution state, but there's a lot going on, and there's a lot we need to make sure, hey, are we going to be accurate, and can we validate that we've actually been accurate in the past, and have we converged on our, with our numerical solvers for our elevation angles, and have we actually aimed the guns, and has the hydraulic responded, all that stuff has to happen. So once we've finished our wait for solution, then we're going to get into, okay, is this accurate enough? Because, okay, if we're talking about a destroyer that's, I don't know, 400 feet, how long was that? 900 feet? I can't remember how long it was. I think it was 400 or 500 feet long. And we're off by 400 feet. I don't have a whole bunch of confidence to take that shot. But as soon as our accuracy, either they stop zigzagging or they get close enough where we don't need as much lead time, all those things come into play, the fire control says, okay, I'm going to commit. And then it goes to the commit fire. The commit fire is sort of like locking in, like, this is going to happen. We're going to take the shot. As soon as the certain amount of time that we set for the buffer, for the lead time, runs out, then fire 1 happens, we reload, and the same thing happens all over again. So that, in a nutshell, is how this is all going to work. And I realized that we've kind of deep dived in, like, to the software solution, and because we're trying to build all these little pieces of a big, relatively big software solution, we don't have the immediate pleasure of watching a ball bounce around on the screen and making a little change and seeing if it still works. And so that's why we're going to not keep hammering on this. I'll still send out all the models so you can dig into them and look at them yourself. But I'm glad that we're working on a tough problem. But I'm also cognizant of you guys and having been in your seat before, when you're learning this stuff and you get too deep in a problem, you just feel like, man, can't we get past this, get our head up so we can see again? And so that's kind of where I think you guys are at. And so we're not going to go further into it. Yeah. So that is my last slide, and I'm happy to be finishing a little ahead of schedule because I want to talk about some other stuff. Okay. So we have talked about all of the main software algorithm stuff I was planning on talking about. But I sound like a salesman, but there's so much more. I would love it if you guys, on your own time and whatever, take a look at some of the different abstractions, like Simulink functions. Super, super cool. Or look at event-based modeling, which makes you stand on your head again, and say, oh, we're not talking about seconds anymore. We're talking about events. But they happen at a certain amount of seconds, and if there's a collision of events. So I wanted to go to, let's see if I can connect to the internet real quickly. I'm kind of going off on a tangent a little bit, so if you guys have a question or something, just shout at me. There we go. So again, I'm not trying to sound like a salesman. I'm just excited for you guys that you're right on the brink of a whole bunch of different things. So I'm just trying to show you a couple other doors because we're not going to come back to the software stuff again. Yeah, it is. It is. Except I don't think the academic package gets propagated more than once a year. So I think the academic package is still 15A, right? Or 16A.
Oh, I haven't tried upgrading to 16B because it's a pain in the ass, but I don't know.
Tell me what you really think.
That would suck.
Yeah. Okay. When I was getting the student versions, they only updated it once a year instead of the twice. But maybe they changed that.
When I first bought it, I got 15B, and then 16A came out right after that. And I'm like, God damn it! But I was able to upgrade to that with no problem. So I don't know if what you mean is that I could only upgrade my next time at 17A, or if there's some other sort of.
That's the way it was when I was in school. I don't know if it's still that way. Yeah, I just figured we started in 16A. I don't want to change in the middle of the seminar. So, right. So
They looked cool though. I just forgot what they were.
So where we're going, the rest of the seminar is physical modeling. And so we've been talking about context, and we have our basics of Simulink, and we have our basics in MATLAB, and some language fundamentals. So we're going to just spend one day in SolidWorks, and there's some really cool things there. But all the stuff that we've been talking about has all been about what you'd say more is pure math, right? We're throwing numbers around, and the computer doesn't particularly care what units we're talking about or what domain we're in. We're talking about flight time of a bullet, or we're talking about lead time of a shot, and we don't have to explain to the system. It's just crunching numbers. It doesn't care. Well, that seems on the outside like, oh, that's just to be expected. But where we're going is with these physical modeling stuff, and there's a bunch of them, SimScape and multibody and driveline. We're going to be using fluids and multibody. Suddenly the software cares, and it's real specific, like to the extent of, are you talking about gallons or liters? Which is really, really great because of the fact that now you can say exactly what you're talking about. I'm talking about, this hydraulic motor has a 90 cc displacement, or I want this flow rate to be 90% efficient at 20 gallons per minute. So we talked a lot about abstraction, and for us to be efficient as modeling and simulation people, whatever you end up doing for your job, at some level you will be modeling and simulating something. It may not be in MATLAB, it may not be even an engineering kind of thing, but you really will. Just take my word for it, at some level. And so what's exciting to me, and I hope I can inspire some interest in you, is the capabilities of creating, not only standing on top of what's built here, but there's always, just like as we've been kind of marching through, and there's, you know, we needed a buffer, there are buffers, but we need a buffer that does this certain thing. So, okay, we'll make our own. We needed something that estimated polynomial coefficients, and we needed 2 imports, not 1 import. Okay, that's fine. We'll kind of hack what they have there and make our own. Well, in the same way we're doing that in the purely mathematical or purely software sense, the physical modeling tools inside Simulink and Simscape have another language. It's a Simscape language, and you can model any domain you'd like, which is really, really cool. So you can inherit, have you guys been through the software, I'm not sure which would be, maybe software algorithms and data structures 1 or 2, where they talk about class inheritance? Does that ring a bell with anybody? Raise your hand if you, I can't see you. I'm just trying to figure out who knows what. So in software, like object-oriented software thinking, you'll create classes of, like, I'm going to create this generic class of a ball. And then I'm going to inherit that class, and I'm going to make a bouncy ball and a bowling ball, right? And they're all round, and they all maybe have a smooth surface, but the bouncing ball has some particular different aspects of it that I want to capture over here, and the bowling ball has some different aspects I want to capture here. Well, Simscape and the language allows you to inherit, like, all of the hydraulic domain, and then you can write your own hydraulic element that does anything you want, which is pretty exciting when you think about it, because maybe you're doing something different. It happens more often than you think. Or maybe, like this has happened to me a bunch of times, I'm using a check valve, which is like a one-way valve. So it's like the hydraulic equivalent of a diode. And there's so many zero crossings. In other words, the pressure differential is changing so fast. I need to remodel what they had to handle the effects happening, because I had these pressure differentials that were doing this. It caused 1,000 zero crossings really fast, and I needed to change and make it more accurate, because that's not what really happened. So I'm kind of excited for you guys, because being, not all of you are engineers, but a lot of you, you know, working in a physical science, the physical modeling tools give you that opportunity to abstract yourself far enough to be efficient, but still lets you extend into whatever you're trying to do. So anyway, that's where we're going to be going next week. And I'm pretty excited about it, obviously. But we'll get into it and try to pull out some generic modeling concepts as we go, and keep things rolling. So thanks for your attention, and that's it for the evening.